epsilon is equal to epsilon naught sine omega t, V is equal to V naught, both are one and the same, it produces voltage itself. LCR. L means it is an inductor, C means it's a capacitor, R means it's a resistor. The effective opposition which is offered by the circuit to the alternating current through it is called as your impedance, where your phase diagram is very much important as well as your graphical representation. Hello everyone, I am Vrinda, Faculty of Physics, welcoming you all. Chapter 7 and chapter name is Alternating Current. So in today's class, we are going to deal with this chapter. So before this, we will have to know the previous chapter, that is electromagnetic induction, out of which we had read about alternating current, that is AC generator, why it is used, the one which converts mechanical energy into electrical energy. So you have derived an equation for an EMF. So what exactly are the uses or the advantage over DC? Let us study. So it can be easily and efficiently convert the higher values to a lower values and vice versa with respect to the current values, okay, voltage. Next, electricity can be transmitted over a large distance, that is economically, that is the electric field which is given in terms of E. Okay, next, it can be converted to DC by a concept called as a rectifier, which you will be actually studying in your semiconductor diode chapter. So what exactly it is? You have full wave rectifiers as well as you have half wave rectifiers. With the help of a diode is this produced. So it can be converted to DC, AC to DC also conversion is possible with the help of a certain called as a rectifiers. The rectifiers are the one which will have a presence of diodes in it. Next, it can be step up as well as step down transformer also can be performed over here. Those are the advantages of AC over DC. Next is, let us just check alternating voltage as well as current. We had derived an equation for alternating voltage. Similarly, we have an equation for an alternating current which you have to know. So for an alternating voltage, we have an EMF concept, that is EMF. We write it as epsilon is equal to epsilon naught sine omega t. So this is an equation. Similarly, for current, you have I is equal to I naught sine omega t, where this epsilon or I are called as EMF or the current. Epsilon naught and I naught are known as instantaneous. So this happens at certain interval of time or certain instant of time, and sine omega t is the phase angle. Sine is the function of the wave. Okay, so that is all about your alternating voltage and alternating current. With the help of these two set of things, we are going to derive certain set of equations. First of all, we go with alternating voltage applied to a resistor. So we have a voltage as epsilon is equal to epsilon naught sine omega t, or it can be called as V is equal to V naught sine omega t. This is with respect to the voltage. So one derivation will be performed. Likewise, you have the derivation for your alternating voltage applied to a capacitor resistor, for which the equations will be finalized and explained to you. So here epsilon is equal to epsilon naught sine omega t, V is equal to V naught, both are one and the same, it produces voltage itself, whose SI units will be volt itself. So as we know, due from the Ohm's law equation, we have V is equal to I into R. So on application for V here, we have V naught sine omega t is equal to I into R. So I retain V naught sine omega t, retain your I, get your R down. So with the help of this, applied to a resistor, when that's the case, the varying is voltage. So we'll have to vary it to a current, because V is equal to I into R. When I is there, it is V by R. If this is V naught, this should be I naught, like this. So I naught sine omega t is equal to I gives you the value of the current. So this means to say that there is no phase difference over in this place as well as in this place. So now it is omega t. Only omega t is the one which lies here. So only omega t is the phase which is present over there. That means to say that in phase diagram over here, you have 0, so 0 to pi to 2 pi, even current as well as your voltage. This is voltage value, this is current value. Both also will be in phase with each other. There is no difference. See, you can see there is no difference between any of the things. All are coming under the same phase. So here, this is all about your alternating voltage applied to a resistor. Likewise, you have to a capacitor as well as for your inductor. You can see that there is a phasor diagram for this. So voltage is here, current is also on top of it, V as well as I both are also on top of it. So here it is phase. This is a phasor diagram, what you call. Actually, there is no leading or lagging. It is in phase with each other. That is, voltage is in phase with the current. Where? Only in case of your resistor. So for your capacitor as well as inductor, you have I is equal to I naught sine omega t plus pi by 2, which means to say the current leads the voltage by 90 degree. Pi by 2 means 90. And you have for inductor I is equal to I naught sine omega t minus pi by 2, which means to say the current lags negative 90. No, current lags voltage by 90 degree. For which for the capacitor leading we have phase angle and the current is shown here, voltage by 90 degree. It is pi by 2. It is 90 degree plus 90 with respect to this current. And next you have inductor. It lags. So this is a phase angle. If this is current, this will be voltage with respect to pi by 2 with the current. This is voltage. So that is how exactly your phase diagram goes, where your phase diagram is very much important as well as your graphical representation. Most common importance is given to the phasor diagram. Okay. Next is what is meant by an inductor. So you have to know what is an inductor, right? An inductor is also called as a coil or a choke or a reactor. It is also called as a passive element, two-terminal component it is. Okay, as you can see over here, these are the inductors. It stores energy in a magnetic field when the electric current flows through the coil. Okay, that's all about your inductor concept. So for which we have got an equation. What is the relation between this inductance as well as the current, capacitance as well as the current, as that of alternating current which is applied to a resistor. Okay, so next we will check on to the alternating voltage which is applied to series LCR circuit, for which we have LCR. L means it is an inductor, C means it's a capacitor, R means it's a resistor. So here we have a AC component, alternating current component, okay, with certain EMF. Okay, so now let us check. This is L, this is C, this is R. How exactly the movement of the current takes place over here, for which we have a diagrammatic representation. It's a fusion of alternating current applied to inductor, alternating current applied to a capacitor, and alternating current applied to a resistor. So for which we have a phasor diagram known as, okay, so here it turns out to be omega t, here VL minus VC, and here we have a notation. So for which we give it as, this notation as VR and this is V naught. Okay, so by looking at all this, we have origin, let me name this as A and let me name this as E. Okay, so this is a phasor diagram of the fusion of all three set, and here we have VL and here we have VC. That is how exactly it goes with respect to the phasor diagram. But we consider only the above terminals for our reference. So just let us see, according to this, like a Pythagoras theorem, if you're suppose considering, so OE square is equal to AE square plus OA square. This is square of hypotenuse is equal to sum of square of the other two sides of a triangle. So now on equating this, you have OE square is equal to AE is nothing but VL minus VC the whole square plus your OA square is nothing but your VR square. When we just write this, VL minus VC the whole square, V is nothing but I and it is R minus IR, both are square and square, plus IR square, which means to say that V is equal to IR, that is from Ohm's law. So in order to check it out, so V is equal to IR in case of resistance, it is R itself. In case of inductive reactance, and in case of capacitance, it is capacitance reactance. Inductive reactance and capacitive reactance act same as that of your resistance. Okay, so you can just equate this. This is just in a bracket. You can just write, this is actually the form of getting OE square is equal to I into XL square minus I into XC square plus I into R square, or you can even write it as I XL minus I XC plus I R square the whole square. Since there is a I which is said to be I naught component over here, instantaneous, so we can just retain everything with respect to I naught. So we have I naught component over here, okay, because your OE square is said to be V naught. All of them turn out to be I naught. So now you have got a clarity on this. So V naught is equal to root of R square plus XL minus XC the whole square, where I is common everywhere, so it's taken towards the other side. So V is equal to IR, you know, as usual. So V by I is nothing but R. So here it is, R is nothing but the impedance what we give Z. So root of R square plus XL minus XC the whole square. So this holds good for the impedance concept. Okay, so this is all about your impedance that is given by alternating voltage, which is applied to series LCR circuit. And suppose if you have to find out the phase angle, so you have tan of phi. So tan of phi is given over here. So tan theta is nothing but opposite by adjacent. So your opposite is AE and adjacent is OA. So tan phi is equal to, you have VL minus VC of OA is nothing but your VR. So phi is equal to tan inverse of VL can also be written as I naught XL minus I naught XC divided by I naught R. So I naught is common, so phi is equal to tan inverse of I naught is taken outside, XL minus XC divided by R divided by I naught here, it cancels out and it becomes 1. So that is all about your phi notation, tan inverse of certain component. This is all about your alternating voltage, wherein you have your impedance as well as to calculate the phase angle. Next is the definition for your impedance, which means to say the effective opposition which is offered by the circuit to the alternating current through it is called as your impedance, which is represented in terms of Z, and that is nothing but Z is equal to root of R square plus XL minus XC the whole square. We can interchange it with respect to the components, but interchanging also doesn't give you any change with respect to numericals because it's of the square. So that is all about your chapter. So in today's class, we have done with your alternating current chapter. That is, we have got the value whenever the alternating current is applied to a resistor. How is it, whether it is in phase or not, all these concepts we have studied, and most of the important concepts of this chapter is covered. Let us all meet in our next upcoming session. Until then, have a good day. Thank you.